we're going to continue with chapter 4, solidification and crystalline imperfection. Seen from the previous class that we have covered the first topic, which is the solidification of metals. So you learned about the two different types of the nucleation process, which is the formation of the smallest solid particle before it starts to grow into crystals and eventually grains. Alright, so you can re-look at those video recordings, refresh what you have learned. So in this video, I will be focusing on the second part, which is metallic solid solutions. So you have probably heard of a solution. Solution is when it's a mixture. It's one or two or more extra components. Okay, a pure metal has only one component. It can be whatever metallic element, but a metallic solid solution will have more than one. Alright, so how do they form this? And we're talking about solid solutions. We're not talking about what you probably learned in chemistry, which is liquid solution. Metals are mixed, of course, they are in liquid form and then they solidify. And then how do they form the solid solution? Alright. Okay, let us first look at the definition of metallic solid solution. Okay, so an alloy is a mixture of two or more metals or a metal and non-metal. As long as there's two or more components and at least one of it has to be metal, it's considered an alloy. Alloy is the common word we use to describe this metallic solid solutions. Alloys are very popular. Alright, they're used in a lot of engineering applications to basically improve the properties of the product that we want. Okay, that includes increasing the strength, having a higher corrosion resistance, etc. Maybe to have a higher melting temperature. Alright, so the components of the alloy depends on what function you want. So some example of an alloy is brass. Brass is very popular. It's made of 70% copper and 30% zinc. And then of course there's our steel. Very, very famous. The most widely used alloy is a composition of iron and carbon. Okay, so a solid solution is when the solid consists of two or more elements atomically dispersed in a single phase structure. Alright, so what is a phase structure? Let's recall phase structure can be the common ones that we have learned. BCC, FCC are two of the examples. Okay, so it means that even though the metal elements have more than one type of element, but they are dispersed in a single phase structure. So the structure does not change. Only maybe parts of the atoms in the structure to the other elements. Okay, that is how you can view the solid solution. It still has the same atomic arrangement. Okay, so the first type of solid solution is called substitutional solid solution. You probably know this word. Substitute is when you replace. Okay, so what's happening is something is replaced. Right, so the one that is higher in quantity. there are only 3 solutes here. More solvent. So atoms substitute or replace the parent solvent atom in a crystal lattice. Remember, it's of the atoms. So the solute will substitute the parent atom. Parent meaning the solvent, the main one. Alright, so what's happening here? Okay, it's important to remember that the structure of parent element remains unchanged because that is the definition of solid solution. It has the same structure even though now it is an alloy. Okay, so you can see that the structure does not change at all. Lattice might get slightly bigger. So what might get slightly distorted. Okay, I'll show you this in the. Okay, so here we have all solvent atoms. The center of the atoms are perfectly arranged. Of course, arrange marbles on a tabletop, you're gonna get this as well. Very nice repetitive arrangement. Okay, so what if you have solute atoms present? See, it's smaller. Okay, so when it's smaller, you can see that the atoms around it, let's look at this, okay, the 6 atoms around it, they are no longer in a nice hexagon shape, whereas here it's a nice hexagon shape because they are the same size. But here, no, it is slightly distorted. You can even see that around the other solute atom. Okay, so this is what it means by the arrangement being slightly distorted but still not changed. Okay, so you can either use a triangle to represent or a hexagon like what I did here. Okay, so that's it. Solid solution. Okay, so can all metals produce? Okay, remember that has to simply replace some of the atoms. So can this be done by all metals? The answer is no. Conditions for solid solubility to happen. Okay, so it's not as straightforward as yes or no. There's actually a range of percentage. Okay, there's a percentage of solubility. If you can recall chemistry, you probably remember how much salt can you put in water. Okay, let's say the water, the solution is sodium chloride, right? Let's say the uh, solution is 50% water, 50% salt. Okay, that means the solubility is 50%. So the same applies for solid solution as well. We have a range of for how soluble each other. The first one, the diameter atom is bigger, if the solute atom is a lot bigger, it cannot fit into this empty space. And if it's a lot, definitely fit, but it will more than slight distortion. It will change the structure, or the structure might collapse and form a different structure. That's why 15%. Okay, the second one, this is obvious. Crystal structures are similar. So if one is BCC, both have to be BCC. Otherwise, they cannot. Okay, the third one is small difference in electronegativity. Why? Because if it's very different in terms of their charge, then they will form a chemical reaction, compound. Okay, if one is very, one is more positive, one is more compounds. So there has to be small difference in their charge. And finally, they have to have the same valence. Okay, this is actually very closely related. They have to have the same valence. Okay, valence here meaning okay, so look at some examples. Here the table shows a comparison of copper being the parent or the solvent atom. Okay, the one is high quantity, and here we have zinc, lead, and nickel being the atomic radius of each compared to copper is 7%. So soluble. Okay, only 38.3. That is mostly because the atomic radius difference is bigger. Yes, it is still within 15%, but it's significant. And it has different electronegativity. Hence why it's 38, but it's still very high compared to copper and lead. Only 0.17%, not even 1% of lead can be in the solution. Only 0.17. Okay, that's very little. Why? Because lead is huge compared to copper and differently charged. And finally, look at copper and nickel. Very small difference in the radius, no difference in the charge, and it is 100% soluble. So you can put whatever amount of nickel you want in a copper, and then it can still form a solution. It's not limited, okay, by the size, by the charge, or anything. Okay, now let's look at the second one of the is the interstitial. If you one on the left is more dense. Around it. That of for the parent atoms has to be much. Parent atom, it can only fit a small solute particle. Okay. Example, let's see. There's also a percentage. So between these temperatures, interstitial solid solution of carbon and okay, so carbon temperature, specifically a maximum of 2.8% of carbon can dissolve dissolve this way, interstitially in iron. Only 2.8. Why only 2.8? Because after it has dissolved, rest to enter for more than 2.8%. So this is the maximum. Alright, that is an example of interstitial solid solution.